is named?
Well, that is
temporarily.
yeah. So. Sorry. So as you see, I'm the caretaker. I am not the program, manager, for this. So I'm not active, as such. Well, hello again. So I will give you a snapshot of our electronics program, and this probably in my opinion, the most important program at AFOSR OSR, because everything that we do here depends on electronics. Because you couldn't, no matter if you run simulations in a wind tunnel or so on, you need, electronics to do it, and be it the workflow that we manage at AFOSR OSR and so on. So, but this is a program with a vision toward high-speed electronics for analog and digital applications. And it's, of course, an area that has wide usage, from be it phased array radar, front-end processing, and your electronics, be it in your wireless devices, etc. And so there are lots of opportunities here for the Air Force to benefit from, and actually the DoD. And this is an area that has very much benefited from scaling. And so before I kind of talked about scaling, but here you're dealing with the ultimate scaling. And so many of you are probably familiar with the kind of alphabet soup of transistors, that you can have FETs and MOSFETs and HBTs and so on. And so so when you think about this program, think about that. So yeah, I guess kind of thoughts about this program, as I go through it, is basically think about transistors, think about high-speed electronics, think about oxide electronics, and then kind of the physics part. It's two-dimensional electron gas, because that in studying that that really helps to understand some basic physics and some very exciting ideas that are out there. So I should not really be giving this presentation. We have a guest speaker, actually, if you wanted to speak, right here in the audience, and that's Jim Wang, who kindly has, actually, he's the architect together somewhat with Kit Reinhardt and Greg Jessen, who was at one time at the Tokyo office, but Jim Wang has laid out the vision for this particular program, and so something happens to me up here, he's the person who will take over. So it's kind of divided into three areas in the THz electronics, and there you can basically think about more traditional materials, the group 4 materials and the group 3-5 such, and the key there is those are usually understood more from the point of being covalently bonded. And the challenges there are to kind of move the devices into the terahertz regime, and to look at the challenges associated with that, which is, for example, perfecting the crystalline structure, the interfaces, this whole business with, again, the 2D, two-dimensional electron, gas at the heterojunction, of these dissimilar, materials. And then the second part is the novel gigahertz electronics, and there we're looking for breakthroughs in transistors, and this time, however, we're focusing on ionic bonds and some of the interesting I guess challenges, you know, as you scale and also go into this particular material system, there's some opportunities, you know, there that really haven't been solidly looked at, you know, in the past, and somewhat similar challenges as in the THz Electronics, as to also looking at crystalline structure and interfaces, you know, but they're also controlling purity, stoichiometry, and the doping, and the basic physical characteristics like electronic, you know, properties. And then the third area is a way of actually almost enhancing, you know, the first and the second, you know, area is reconfigurable electronics, and so exploring you know, some of the novel materials, you know, that are out there, be it, you know, metamaterials, multifluorics, nanomagnetics, and you know, trying to kind of understand the basic electron, photon, plasmon type of interactions, and, you know, possibly add those, you know, to those, you know, other, you know, platforms. And so this is a particular chart here that shows the cutoff frequency versus breakdown voltage, and you know, in a way the breakdown voltage, you know, is kind of a measure of the power, and there's a chart from DARPA, and it basically shows you the different, you know, technologies here for the THz Electronics, or high-speed, you know, electronics. That you basically have the silicon here, and that's basically has been pursued by, you know, industry, and as you see, you know, that, you know, if you want to operate at higher power and so on, well, the silicon is not, you know, doing it for, you know, for you. And so that's why in the past, you know, we've made decisions to go into the 3-5 system, the indium phosphide, you know, based system, and then also the gallium nitride, you know, system. And actually it turns out that AFOSR was very much on the forefront, you know, of that in back in the 92, 93, 94 time period. We really pushed that particular area in developing the material development for gallium nitride. But, you know, over the time we've kind of basically focused more on, you know, understanding the materials and doing some reliability, you know, programs, while DARPA and ONR end up, you know, pushing it, you know, forward into you know, particular, you know, device, you know, demonstrations. So in trying to understand, or our direction here, oh, I guess I just realized that I maybe skipped over, you know, one particular slide. No, maybe not. Okay. In trying to understand our direction here, in trying to explore some opportunities, is we want to look at high K dielectric materials, and then again, you know, this whole area of, you know, interfaces, you know, different kinds of material, different alloy, you know, systems, and, you know, understand the two-dimensional electron, you know, gas, you know, there, you know, to advance the transistors. And as you know, as you see there are lots of reasons here as to why we want to, you know, do that. You know, from from sub-millimeter wave radar and imaging to various, you know, front-end data processing. And yeah, this chart over here is basically addresses it from the silicon side. I guess one thing I should say, just over the last 4 days, there's been some amazing developments in the news on CMOS. So in a way, I did say, so, you know, here that's more of kind of an industry thing, but there's actually a lot of on the silicon germanium, you know, based electronic systems. There's been some making some amazing devices here, and that been highlighted in the news. Anyway, this is just to basically show you the kind of a basic transistor, you know, structure, you know, where where you have the source, the drain, the channel here, and then this gate structure. And so as we, so this is a representation of kind of Intel's high K FinFET, and to observe here that the whole gate structure has become somewhat complicated, and as we go to smaller dimensions, and so and we're going down to in the direction of these things being in the order of nanometers, thin, and such that tunneling effects take start affecting how the device performs. And so the commercial industry is also looking at solutions there with dielectrics, high K dielectrics, and so on. And so there's some possibilities there with the indium gallium arsenide and quantum well fin. But so this is so it's not that we're supporting this particular area, but there are opportunities to learn from industry as to what they're doing in pushing this. Like for example, their wrapped type of configuration. So the materials, again, kind of focusing somewhat on the nitrides and the various heterojunctions, and so there are opportunities here, as you can see from this lattice constant versus band gap energy, that you can have a certain amount of, I guess, space here where you develop, these material systems, and because they don't line up completely with the lattice constant, you end up having strain, and so you have to deal, with that, and as a result, there's challenges, like the highly strained growth, single phase, ternary, and the P-type, doping. And so the problem is that if you have, I guess, elements, that are maybe smaller in size than others, and so then, these problems become, even more challenging. One individual that's been able to address some of these challenges has been Jim Speck. This kind of shows X-ray diffraction that kind of confirms being able to grow very nice indium aluminum nitride on gallium nitride. But if you look at some various microscopy transmission electron microscopy, you find that there's all kinds of defects as such. And if you look further, you find that you have this kind of nano network where some areas have high concentration of indium, other lower concentration, and that's even more confirmed than with atomic probe type of analysis. And he was able to address these by going or the challenges of growing these materials by going to ammonia-based MBE and MOCVD approach. Other challenges, like say, were with P-type, doping, and so on the right side there for different types of concentrations or different makeup of indium gallium nitride, you have very nice crystalline structure, and if you dope it at the right level now, there's actually been a problem for decades here. There's a whole idea of P-type doping in the 3-5 systems, and so it kind of continued here with gallium nitride, and but they were able to get that parameter space where they're able to get constant resistivity. Hades Morkosh is trying to basically understand the whole business with hot electron and phonon interactions, that as you pump these systems with hot electrons, then the phonons, the optical phonons that are generated, the only way they can kind of lose that energy is through going through to acoustic, phonons. And so it was kind of critical, kind of investigation. We actually ended up working with an international group here to further understand the gallium nitride, system, and in this particular case, I think it ended up, that we had to make some layers a bit, thicker than we thought, instead of going to thinner, layers to get the ideal structure. Again, quickly running out of time here, that we've also looked at engineering various structures and so on to try to achieve higher limits, cutoff frequency limits, for some of these devices. So let me jump then to the lots of exciting things here with this particular area with the gallium, with the GHz electronics, that there's opportunities here with oxide electronics to address this area to move into the higher frequencies. And there have been things done in the past in the area of oxide related work and so on, but it's been primarily at the below 1 gigahertz. And so as a result of some developments within the RY, within the AFOSR Research Lab, on the zinc oxide system for a zinc oxide MOSFET, some exciting results came out that's made us looking at the oxides in pushing it here into the higher frequency regime. And as you can see from this particular chart, there are lots of, by going to the oxides and so on, that there are lots of, because you're doing with the transition metals, mixing them with oxides and so on. There are lots of different opportunities, and yes, there's some, like for example, on this the heterojunction here, this particular one with the magnesium zinc oxide and the zinc aluminum oxide and the strontium titanium oxide, that I think the two-dimensional electron gas is actually higher than in gallium arsenide, and so there's some, let me see here. And from this particular chart, again, there are opportunities here to have various ternary, quaternary of these systems, just depending as to how you mix which particular elements, that you look. And some people familiar with the ionic bonding and covalent bonding, will say, why go to this particular system? Because in a way, it has a lower mobility, and but it's an opportunity to explore as to what is possible, here in pushing that element, of it. And so covalent, usually higher speed, and because of that, in ionic you have more of a hopping, conduction and so on. But the wider band gap, and then there are a whole series of other reasons as to why you want to move into this particular material system. And so we're doing lots of basic things, like Dave Look at Wright State University is looking at various fundamental electronic properties, trying to determine the effective mass, for example. And as indicated in RY, we have an exciting project here where they've been able to demonstrate record performance, and they're moving forward with exploring this particular material system. Very much an area here, in talking about these oxide, is this phase change, the ability to change from, I guess one thing that, let me see,
Well, you don't have time to go back.
Yeah. Anyway, there's an element called cutoff on and off, ratio, and so if you can take some of these materials and go from from insulator to metal and so on, you have a much higher on-off ratio, and so that's one aspect to explore. I'm not going to say much here on the reconfigurable electronics. Again, there are opportunities here to to look at phonon, plasmon, electron, kind of interactions, even the magnetic, regime, to bring more functionality, to the other areas. Topological insulators is potential to look at, at that in a system also. So within, the program, that within AFOSR, there's, interaction not only here, but also with our international offices. And one of the, I guess, really good intersection is with Dan Green over at DARPA. He used to be at ONR, now he's over at DARPA running the next, program. And then the NSF, and one element that I maybe didn't highlight as much because we're still waiting for the programs to kick in, but we do have a joint program with the NSF on 2D materials and devices beyond graphene, and so that should add another element to all of this. So I'll leave it with this, that, like I say, there are two main areas here besides the THz gigahertz, and you can also see it as covalent versus ionic semiconductors, and the common element there is possibly the complex oxides. But there are also other opportunities within the program. But anyway, thank you very much for your attention.
All right, any quick questions? No? Okay, then I guess we'll move on. Okay, the next speaker is going to be Ali Seer.
I will be reporting on aerospace materials for...
You gotta wait until you get the mic.
Yeah, sorry.
I still will be doing the same. Thank you.